This is Porterville College, Physics 104A, Chapter 11, Homework Solutions. Chapter 11 is Rotational Vectors. We start with number 13. A car is headed north at 70 kilometers per hour. Give the magnitude and direction of the angular velocity of the wheels. The angular velocity, omega, is the linear velocity divided by the radius of the wheels. So you have to convert linear velocity to 19.4 repeating meters per second, divided by the radius 0.31 meters. And we get 63 radians per second. Now the direction of the angular velocity, if the car is headed north, and here's my map right here, north going up the page, then you think about which way the wheels are rolling. And the right hand rule, if you take your right hand and you curl your fingers in the direction, see if I can do this for the camera, it might be a little out of focus. Okay, curl your fingers in the direction that the wheels are going, and your thumb points to the left on the page, which is the westward direction. So the angular momentum, the angular velocity is towards the west. Number 14. If it makes a 90-degree left turn lasting 25 seconds, determine the average angular acceleration of the wheels. So average angular acceleration is difference in angular velocity over time. It's the difference in those vectors divided by time. I solved number 14 in a graphical way. When we go to number 15, a different problem, I'm going to solve it using the x and y component vectors, so more analytically. So you can compare between how I solved number 14 and how I solved number 15, and you can use either solution for either of them. But here I do it more graphically. I have omega naught going to the west, or going to the left on the page, and that's what we found in in number 13. And then it makes a left-hand turn, which means omega 1 is going to be going, it's the same magnitude, but it's going to be having turned left 90 degrees, so going south. So here's omega naught, here's omega 1. Now graphically, if we're going to do the difference of two vectors, omega 1 minus omega naught, that's the same as omega 1 plus the negative of omega naught. So to find the sum of those vectors, omega 1 plus the negative omega naught, which is omega naught but facing in the reverse direction, the sum of those vectors is the change in omega. What we have is an isosceles right triangle here, 62.72 on one side, 62.72 on the other side. You can use Pythagorean theorem and find that the change in omega is 88.71 radians per second. So that goes right here, 88.71 radians per second, occurring over a time of 25 seconds, so you divide those, and you get 3.5 radians per second squared. And we can see graphically it's down and to the right at a 45-degree angle, so it's in the southeast direction. Number 15. Number 15 asks for angular acceleration, average angular acceleration, just like number 14 did, but I'm going to solve it non-graphically, using just the vector components. So for 15 we have omega naught, and it gives it in RPM, revolutions per minute, so you're going to need to convert those to radians per second. So you should get omega naught is 4.712 j hat radians per second. Omega 1 then is 6.28319 I hat radians per second. And those directions come from which way it says the axis is going, vertical and then horizontal. So average acceleration is the difference of the omegas over change in time. Omega 1 minus omega naught. And here, instead of like in number 14, I solved it graphically, I just plug in the components. So I use my stacked vector notation. So omega 1 is 6.28 in the I hat direction, 0 in the j hat direction. Omega naught is 0 in the I hat direction, 4.71 in the j hat direction. And you just subtract those and divide by 15 seconds. So here are the vectors after subtracting. So this vector in the numerator represents the change in omega. Divide by 15 seconds, and we have 0.4189 I hat minus 0.314159 j hat radians per second squared. Now the question is asking then for the magnitude of the acceleration, of the average acceleration. So we can use Pythagorean theorem on those two values and get 0.52 radians per second squared. To find the angle, the tangent of theta is the y component over the x component of acceleration, and we get that it's 37 degrees, actually negative 37 degrees from the x-axis. Number 17. We're given the force, we're given where it's applied, find the torque about the origin. And for part A, the force is 12 I hat newtons. So R, the lever arm, is 3 I hat plus j hat meters. And we're going to use the idea that torque is the cross product of R and F. For part A, I've just drawn the picture so you can see the vectors. R going off in this direction, F along the x-axis. And if you use the right-hand rule, you take your right hand, curl your fingers from R to F, and you'll see that your thumb goes into the page. And so we're expecting that torque is going to be in the negative z direction. And you don't need to do that, but it's sometimes nice to know what you're expecting it to be, the negative z direction. Well, let's solve it. Torque is the cross product of R and F. I taught in class to find a cross product by setting up the determinant of a matrix. The first row is always I hat, j hat, k hat. The second row is the R vector, so 3, 1, and 0. The third row is the F vector, in this case 12, 0, and 0. Finding the determinant of the matrix, first your I hat component. Remember the way we find determinant of a matrix. You, first of all, with I hat, we're going to block out that row, block out that column, and we see what's left is the matrix 1, 0, 0, 0. And we take the determinant of that 2 by 2 matrix by doing 1 times 0 minus 0 times 0. Then for the next part, the j hat part, remember to subtract this. So when we block out the row and column that are in j hat, we're left with this matrix, 3, 0, and 12, 0. So it's 3 times 0 minus 0 times 12. And remember, we have to subtract the j hat component. Then plus the k hat, 3 times 0 minus 1 times 12. Most of these terms go to 0. What you're left with, just the only non-zero part, is right here. So we get negative 12 k hat. And as we found graphically with the right-hand rule, as we expect, it's in the negative z direction. So negative 12 k hat Newton meters. Part B has us solve this with the force going in the y direction, 12 j hat. So the torque is the determinant of this matrix. I j hat k hat, 3, 1, 0, but now force is 0, 12, 0, because the 12 is in the y direction. solve that determinant and you should get 36 k-hat Newton meters. And you can also check these graphically if you want to. Do just like I did the first graph, but make force go up the y direction, and then when you curl r into f, you can just curl r into the y-axis, and you see then that the thumb comes out of the page. Part C, we have force in the k-hat direction, so force is 0, 0, 12. You solve that determinant, and you should get 12 I hat minus 36 j hat Newton meters. Number 20 is an exercise in dimensional analysis. Express the units of angular momentum first using only the fundamental units, kilogram, meter, and second. I'm going to show one of many ways to do this. Whenever you're doing dimensional analysis and you want to break something down into its fundamental units, the first thing to do is just to think of any equation, the simpler the better, that uses that quantity. So for angular momentum, one that comes to mind is that angular momentum vector is the cross product of r and p. You could also start with dl over dt equals torque, but I start with this one. Now for dimensional analysis, we don't care about any constants, we don't care about any dimensionless quantities. So I've shifted from using equal signs just from using is proportional to. L is proportional to R times P. Which is proportional to, well, there's R. And then I think, how does P break down? Well, I remember that linear momentum is m times v. And again, I just think of any equation, the simpler the better, that uses that quantity. So P is mv. So now I've got that dimensionally linear or angular momentum is the same as r times m times v. Then I just break those down. R is a distance, so that's meters. Mass is, well, that's mass, so kilograms. Velocity is distance per time, so meters per second. This is angular momentum broken down into its fundamental units. So clean it up and we say kilograms meters squared per second. Another one we could have done is use the equation L equals I omega. We know that I, when we first defined it and came up with rotational inertia, is mr squared. And even if you don't think back to when we first defined it, if you just look up in the chart where there's the sphere and the rod and all those things, it always is some coefficient times dimensionally a mass times a distance squared. So mr squared. And omega is radians per second. So mass becomes kilograms, radius squared becomes meters squared. Radians per second, remember radians is a pseudo unit, it's dimensionless, but there's the per second, and you're still left with kilograms meters squared per second. Part B asks us to put it in terms of newtons. So here's one way to do that. We start with kilograms meters squared per second. And so we are asked to involve newtons, so let's multiply this by 1. And it's a special form of 1. What I've done in blue here is equal to 1. I've, recognizing that a newton is a kilogram meter per second squared, I've multiplied by a newton, and then I've divided by a newton, or I've multiplied by the reciprocal. So when I do that, I've introduced newtons, and now I can cancel out a bunch of things. The kilograms go away, 1 power of seconds goes away in the numerator, or in both numerator and denominator, leaving 1 in the numerator. 1 power of meters is left in the numerator, so we're left with newtons meters seconds. For part C, we're asked to find angular momentum in a form involving joules. Well, if you recognize that a Newton meter is a joule, you can just combine these to be a joule second. Number 23. You have a hoop, there's its diameter, convert that to its radius of 45 centimeters, rotating at 170 RPM about its central axis. What is its angular momentum? So we need to go back to chapter 10, look up in the table. The moment of inertia of a hoop about its central axis is mr squared. There's the mass times the radius squared, so we get the moment of inertia is 0.1296 kilograms meters squared. Omega, we need that in radians per second, so I get 17.80236 radians per second. Then the angular momentum is I times omega. Multiply those two numbers, we get 2.3 kilograms meters squared per second. We want to know the direction of that vector. You can see in my picture as I have it spinning, use the right hand rule, curl your fingers in the direction that it's spinning, and the thumb in the direction I've drawn it. Thumb comes out of the page, omega vector. And this equation right here, a scalar multiplication of a vector, means that the angular momentum is going to be in the same direction as the angular velocity. So you can just say it's along the axis. Number 25. A potter's wheel. So this potter's wheel, for one thing, we don't have to figure out its initial moment of inertia. It's already given to us, so we just accept that number. But that's going to change once this lump of clay gets dropped on. We're going to take the lump of clay as a small point particle, so it's a mass at some radius from the center. Well, this is a conservation of momentum problem. L naught equals L1. L, angular momentum, is I naught omega naught, and then equals I1 omega 1, where I1, this is the angular momentum after the lump of clay has been dropped. It's the original, this is the moment of inertia after the clay has been dropped. It's the initial moment of inertia, I naught, plus the additional moment of inertia that's added by that lump of clay, mr squared. So we solve this equation for omega 1. Omega 1 is I naught omega naught over I1, where I1 is I naught plus mr squared. And in the lines below, I've solved for I naught. Oh, that was already given. I've converted omega naught to radians per second. There's mass. There's r. So you plug those numbers into this equation, and you get omega 1 is 1.8266 radians per second. Since the question was given in the form of revolutions per minute, it starts out by saying it's spinning at 19 revolutions per minute. We want to give the answer in that same format. So convert this back to revolutions per minute, and you get 17.4 revolutions per minute. So it's slowed down. Number 27. Cloud of interstellar gas collapses to form a star. Find its rotation period. Okay, conservation of angular momentum. I naught omega naught equals I1 omega 1. You can solve this for omega. I've done something a little different. I've just converted it automatically to the periods, because the question is asking about period. So you can save this step to the end, but I just went ahead and did it here. recognizing that omega is 2 pi over the period, because omega is 2 pi times frequency, f, and frequency is the reciprocal of period, so omega is 2 pi over period. And when I do that, the 2 pi's go away, they divide out, and what I'm left with is I naught over T naught equals I1 over T1. The question is asking us to solve for the final period, so T1 equals I1 over I naught times T naught. So we assume a uniform spherical cloud, which we go back to chapter 10, look up in the table, that is we can take it to be similar to a solid sphere. 2/5 mr squared 1 for I1. I naught is 2/5 mr naught squared times T naught. The 2/5 divide out, the m divides out, so the mass of the cloud is not relevant here. And what we're left with is that the period is the original period times the ratio of the radii squared. So we plug in those radii. The final radius is 7 times 10 to the 8th meters. The original is 1 times 10 to the 13th meters. Don't forget to square it. Times the period, 1.4 times 10 to the 6th years. So the answer we get will be in years. 6.86 times 10 to the negative 3 years, and so 2.5 days is the rotation period of this star. So the star, in having shrunk down considerably, which used to have a period of almost 1.5 million years, now has a period much shorter of only 2.5 days. Number 32. More of a math problem than a physics problem, but it'll help you with your facility in using vector products. Show that the dot product of A with the cross product of A and B equals 0 for any vectors A and B. I'm showing two solutions, a short one and a long one. So let's do the short one first. A dot A cross B. I'm going to show that that's equal to 0. And I'm going to call A cross B vector C. Graphically, if I draw any vector A and any vector B, A cross B, the vector C, use your right hand, curl A into B, and that gives vector C in the way I've drawn it coming out of the page. And what this reminds us of is that the cross product of any two vectors is going to be perpendicular to both of those vectors. So C really had only two choices, either going into the page or out of the page, that would make it perpendicular to both A and B. And right-hand rule says that it's coming out of the page. But here's the important part. Vector C is always going to be perpendicular to A. Now, let's do the dot product with A and C. Dot product of A and C is A times C times the cosine of the angle between them, which is A times C times the cosine of 90 degrees, which is equal to 0. It's important to note here that the dot product of any vector, let me say that again. The dot product of any two vectors that are perpendicular will always be 0. Okay, that was the graphical, the short way. Let's do it the long way, with the vector components. A cross B, you set up the matrix and take the determinant of it, so I hat, j hat, k hat. The components of A are A sub x, A sub y, and A sub z. The components of vector B are B sub x, B sub y, and B sub z. So we take the determinant. I've set it up in the stacked vector notation, so this first row is the I hat component, the second row is the j hat component, the third row is the k hat component. So we start with I hat being ay times bz, minus AZ times BY. The J hat component, the second row, is AX minus BZ, AX times BZ minus AZ times BX. But remember, you need to subtract the J hat component, so I've changed the signs on those. The K hat component, AX times BY minus AY times BX. So this is the vector notation for A cross B. I move down here to this line, and then I'm going to do the dot product of A with that vector. So AX, AY, AZ, dot product with that vector. And remember how to do the dot product. It's the product of the x components, so AX times AYBZ minus AZBY, plus AY times negative AXBZ plus AZBX, plus AZ times AXBY minus AYBX. So that's these two lines that I've given here. Distribute those A's and you'll see that basically everything cancels out and it'll go to 0. Number 44. A force is applied at a point 20, produces a torque 4.6 k hat about the origin. We're given the x component of the force. What angle does it make with the x-axis? Okay, so torque is the cross product of r and f vector, and we're given that it's 4.6 k hat. I've set up the matrix right here to find that cross product, I hat, j hat, k hat, 2, 0, 0. I wrote fx, fy, fz. If you want to at this point for fx, you can fill in that given value, 3.1 newtons. I didn't. It's really not going to affect it. Eventually we're going to have to add it in, and I just add it in later, but you could make this 3.1 newtons right now. When you take the determinant of this matrix, you're left with, in the j hat direction, negative 2 times fz, plus in the k hat direction 2 times fy. Now, this is equal to the torque. It's equal to this. So we're going to set this vector equal to this vector and see what happens. So here's what I got from the determinant of the matrix. Here's what's given in the given information, the torque, 0, 0, 4.6. And let's see what it tells us. It tells us 0 equals 0. That doesn't tell us anything new. Negative 2 fz equals 0. Well, that tells us that fz equals 0. 2 fy equals 4.6. That tells us that f sub y is 2.3 newtons. So here we're given all three components of the force. We were given from the beginning that the x component is 3.1 newtons. Now we know the y component is 2.3 newtons. And now we know the z component is 0 newtons. So I've drawn a graph of this force vector. Since its z component is 0, it doesn't come out of the page any. And the angle is the arctan of the y component of force divided by the x component of force. So it's a 37-degree angle. That's the end of the Chapter 11 homework.